Yeah, more of you are happier than I thought you'd be. So. I like when it snows a lot because I make snow caves. A whole bunch of shoveling, let it settle and then carve it out, and made the biggest one I've ever made this year. And I was already happy. But with all this other recent snowfall, I've started a second edition, a second wing. And it's about big enough I can start digging that one out. We'll connect the two. Have fun. My daughter and I slept in it a couple weekends ago. It's warmer inside it then. It's always above freezing inside them. It's still cold, yes. But to begin with, I chose 3 clicker questions from some material at the chapter 5, so you can dig that out. And I checked before class off of last sessions, and there are those 5. We've narrowed it down to 5. That's good. Devices, responseware, mobile, or clickers that are unassigned. In other words, I'm getting responses from these 5 ID numbers, but I don't know who you are. Thus, check your ID number in your account or on the back of your actual clicker. That's the convenient one. If that's one of you, please contact me so I can connect you up or have you do the registration process correctly. The way to double check is log into your turning account. That was redundant. You should have a nice, I think it's a green check mark at the moment with a device, and check your ID. If it's there and that's one of you, then did you go in through Canvas modules? That's how it connects it to your name. If not, maybe just try it again. Either way, you can contact me. So anyway, those 5 people, I'm getting responses, but you won't get any credit for any of it until I know who you are. Oh, lights. All right. Before we start reviewing everything, we'll just review a little more 5 since it's most recent. So here's one of some stuff we did last lecture. Air escape in a balloon. Figure out some of the forces. Let you read that and log in. I'm curious, how many have never blown up a balloon and let go of it to watch it go? Anybody? Yeah, that's what I figured. All of us have done that. Well, this is just asking what actually propels the balloon and makes it go? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, and most of you B, and that's correct. What's the balloon do to the air that started out inside the balloon? Yeah, the pressure, which we're going to learn is related to force. So it exerts a force over that area of the air and, yeah, pushes it out. According to Newton's third law, all forces come in pairs. So if the balloon exerts a force on the air and ejects it, the air pushes back on the balloon. And it's that force that propels the balloon. Questions? So what? I think the other answer was C. I'm trying to think, to help you. the air still in the balloon. I guess until it gets interacted with. Remember, if that air doesn't possess force. You can't possess force. Six, 5, 4, 3, 2, 1. Overwhelmingly D. I like this though. Most of you are C. Mosquito is going to die and the truck could care less. So the mosquito must be feeling more force. That's what people are thinking. Well, that's why you're in the physics class. So with your physics hat on, it's like, but wait, Sir Isaac Newton said, or at least Adam Beehler said, no, the force has to be the same. If the truck pushes on the mosquito, then the mosquito pushes back on the truck. So why is the truck not harmed? Exactly. It has more mass, more inertia. It resists that change in motion. So it will be accelerated, change its motion, less. But the poor mosquito, which hardly has any inertia relative to the truck. Another way to think of it, remember my medicine ball and coffee filter? I was hitting them. And you can hit the brick wall and the medicine ball harder than you can hit a coffee filter, because the coffee filter gives way. It can only push back so hard because it has little inertia. It's kind of that way with a mosquito too. But that's enough force to hurt the mosquito still. It's hardly anything for the windshield. Question? Okay, one more. And I'm thinking good thoughts for you, Brenda, because this is a component question. See what you guys said. D. Good. You can put your clickers away. So if it's 40 one way and 30 the other, then the net is 10. Do you see that? If you add 40 and you put 30 on top of it, the most you could ever get is 70. So yeah, 80 is bogus. So somebody described to me, how could you get 50? At an angle. Yeah. I don't expect you to know which angle, but does anybody already know? $30, $40. Yeah, if you got like a cart here and something's pushing at 30 and something's pushing at 40, which way will it go? Draw those parallel lines. Or again, it's going to go, this tries to make it go to there, and this one tries to make it go to there, so it's going to end up, there's the resultant. And that would actually end up being 50 newtons, which you could use Pythagorean theorem to figure out. Or that's one I've memorized. On a right triangle, if you have sides 3 and 4, the hypotenuse is 5. 3, 4, 5. It's just one of those basic ones that. But didn't need to know it exactly. But you're right. That one would be a right triangle. In case you're interested. Questions? Did you get it right, Brenda? Yeah. Okay. Well, since I started with something, how about you guys? What are your questions? What were you wondering about this weekend? Oh. So you're all feeling confident you'll get 100% on the test. Huh? Yeah, I know that's a lie. Not that it can't happen, but that's how you feel. Yeah. Cart. Oh, the horse and the yeah. That always gets people. Not exactly. Just say it again.
Because it's basically P and F, it was F minus P is the answer. So I expected it to be like a force attracted by its carrier. They're acting on
I'll draw that one. I think it's worth it. So we had, and my artistic skills. Okay. Yeah. Anyway, maybe some ears will help. Okay. So, silly me made it a little smaller than I wanted. Okay, they called, there's a bar here. So forces. It had big P. Thus, that's the horse is being pulled back by the cart with the force P. So the action-reaction, the pair is, he's also pulling the cart, force P. They're on different bodies, but they're equal and opposite. Here, the horse is moving forward because he's pushing against the ground. So he pushes on the ground with a force big F. Thus the ground pushes back on the horse, big F, thanks to friction. Did you ever think what life would be like without friction? People often complain, it wastes energy. We can't be efficient. Yeah, I don't know, maybe when you're falling asleep tonight, you wouldn't be able to walk. You'd never go anywhere, right? You'd have to propel some gas out the back end. What's that? Yeah, climbing, my daughter would be sad. She's into mountaineering. Writing, we couldn't write. Do you know, the pencil lead or the pen? It's friction between them. There's lots of things. So that opposition's good, I guess. Okay, and over here, same idea. That one's the little f. So we have 3 sets of pairs, blah, 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 and they asked you, in the horizontal direction, how many forces are exerted on the cart? 2. Big P here, and little f there. Friction holding it back, horse trying to move it forward. Those are the only 2 acting on the cart. Thus, for the second part, what's the net horizontal force on the cart? Somehow these have to sum up to give us our net force, right? Well, it's being pulled with P, and F is trying to go back. There you have it. If we assume the horse is gonna move it, and it's gonna move that way, and generally to the right's positive, but there you have it. Somebody did ask me through an email so this would be net force. If it was this, then you'd end up with some negative net force with this setup. But if you defined to the left as negative, but for this question, the author was assuming we're moving to the right, big P is going to be bigger than F. You usually subtract the small one from the big one. Does that help? Other concerns? Great. Yeah. Oh, okay. If you're going to switch, then I'm going to do this one first, and then we'll do 12. Because I put new batteries in it. So it was kind of wussy last time. So yeah, much better. So it's blowing air that way. You can see it having an effect. So cart on air, air on cart. Cart moves. And we already saw this. If I blow on the fan sail, then air on cart, it moves. The cart also, though, slows the air down and is pushing on it that way. So when you combine them, how many forces will be acting on the cart? What for? Let's name them. Okay, the fan's pushing on the cart. The air is pushing on the cart. All right. The air from the fan. That's right. So the fan pushes on the air, but that's on the air. So that air pushes back on the cart. So that's one. That's the air that the fan pushes, though, travels over to the sail and pushes on the sail, which is now part of the cart. So that air is pushing on the cart also, but in the opposite direction. When it left the blade, it's pushing back on the cart that way. Yes? When it gets over to here, it's pushing on the sail that way. Those are the 2 on the cart. The other 2 are back on the air itself. I've ignored friction. So technically it's there too. You were thinking that. Which would have been technically 3. Because it's pushing on the ground's pushing back on the cart. So when you turn it on, those 2 balance, doesn't go anywhere. And in way of review, it's not moving. So do we have friction? What 2 types of friction are there? Static and kinetic. And static is when it's not moving. So friction is a force whether it's moving or attempting to move. So until it starts moving, when we started to slide something, and before it breaks free. So there can be friction even though it's not moving. Number 12 on this last homework. Two people of equal mass attempt a tug-of-war with it changed numbers, 18-millimeter rope while standing on frictionless ice. So you don't have to worry about the floor. When they pull on the rope, they each slide toward each other. How do their accelerations compare? Well, all right. Where'd you start?
Well, I assume the first question would just be like if that's the mass, like who has the greater mass, because one with bigger mass has less acceleration.
That's right. If they had different masses, then that would affect their accelerations.
But that answers don't seem to at least.
So you were thinking of this, right?
Yeah.
Good. But it said for them, two people of equal mass. All right. Basically, that just made it easier for you. So how do the A's compare? Ta-da. Sometimes we read too much into it. Now the key here, though, I want to emphasize is when you're doing a tug of war, it's that force that's the same. What if you had, me and little Timmy? Who can pull harder? Oh, thanks for the vote of confidence. The way I asked it, I can pull harder. I hope. But when we're pulling, though, you guys want to come do a tug of war? Who wants to have some fun in class? You're always sitting in class bored. We can have a tug of war right now if you want. I'll let you guys do it, not me. Okay, Mark, you get that in. Who's going to help Mark? Need somebody on Mark's team and then another team. I don't care how many. Come on down if you want to play. I know it's when I do this with pre-college students. Everybody wants to volunteer. All right, we got that side. Who's going to come help me?
I'll be little Timmy.
We can make it equal and fair. This is fun.
Yeah, but where's the fun now? Bets have to be made somewhere. We need a clear favor.
Yeah, and somebody has to be a referee. I better. Then I'm going to help you. Come on, I can tell you want to. Here, start closer. That way you guys, you have room to go or whatever. All right, tell me when you're ready. Well, you look ready. Get set. Go! All right, come back to the middle. Who's pulling harder? This team? No, that's the thing. If they're pulling, technically, they're pulling on the rope this way. So what's the rope do? Pulls back on, equal and opposite. Well, that puts tension in the rope. So that same tension is pulling on them. So what do? They pull back on it with the same tension. So they're essentially pulling the same force. You know how to win a tug of war, though? Friction between what? Yeah, your feet, the floor. People that win tug of war realize it's your legs, not your arms. Sure, if you do an initial jerk, you might be pulling slightly more than they are at that moment. But generally, this is nice and taut, and you're not moving very fast. It's who can dig into the floor and get some friction. Thinking of that, try it again. Ready? Set. Go. And I don't have friction, so obviously it's not working. Thank you very much. Appreciate the helping. So in the homework problem, though, it said frictionless. So they were going to just slide and come together. Yeah, if you ever get in a tug of war again, I guess. Or you have to pull your car out because you got stuck, Don't waste your arm strength. Just hold it tight and dig in. Use those big leg muscles. It should be more effective. All right, what else? What else has been bothering you? I can help clarify. Yes? Oh, based on how fast it's moving or something, where will it be 4 seconds later or something? Okay. Thank you. Let's make up some numbers then. Let's say something's moving. You're going 8 and 50 meters per second. Let's say that's your velocity. Let's just say if you're going 50 meters per second, where will you be? What will your position be 4 seconds later? Start easy. So you're going 50 meters per second, and you're going to do that for 4 seconds. Where will you end up? 200 meters. Two ways, conceptually. Remember, velocity is a change in position. You're going to change your position 50 meters every second. So if you do 4 seconds, you're going to do that 4 times, and it'll be 4 times 200 meters. Well, that's exactly how they got the equation that's in your book, and we've written up here. To help you remember how we get there, velocity is a change in position with time. So what's your change in position? It's velocity times that time, which is what we just did, 50 times 4. But some people, that sticks in their brain better. They like equations. What if, let's start at 50 meters per second and accelerate at 10 meters per second. See what we can figure out now. After 4 seconds, what do we know? So we're starting at 50, and we're going to accelerate for 4 seconds. Tell me something we know.
After 4 seconds, you'll be at 90 meters per second.
And how'd you get 90 as the final velocity? Very good. So again, acceleration is the change in velocity with time. And we're going to change 10 meters per second every second. Since we're doing that 4 times, 4 times 10 is 40. We should be going 40 meters per second faster than we started as. Yes. Or, if you prefer, acceleration is a change in velocity with time. So what's the change in velocity? That acceleration times time. 10 meters per second for 4 seconds, 40. So we're going to change our velocity by 40 meters per second. Add that to the initial, we're at 90. Did I say any of that too fast? Okay, could we know how far we've gone? A harder one. Saved it for last. Okay, we'll do the average. What's the average velocity for that 4 seconds? Yes. If we started at 50 and ended at 90, just split the difference. You add them and divide by 2, or right in the middle. 50 plus 90 divided by 2, which is going to give us 70. Or you can just see that's in the middle. That's why I chose easy numbers. So if you went 70 meters per second for 4 seconds, 70 times 4 is 280. There you go. So you went 280 meters while you were accelerating. Or the equation that guides our thinking of how far did you go when you're accelerating? Plug them in there, and you get 280 meters. Let's see. 10. Half of 10 is 5. 4 squared is 16. 16 times 5. Yeah, 80. Good. It works. You're going, no, no, it's 280. See the connection? That's how far we went accelerating. Just due to the acceleration. And this brings a good point. That acceleration for 4 seconds got us to go 80 meters. Do you get that part? So how do we end up at 280? Yeah, because you started at 50 meters per second. Remember before we accelerated? We went 200 meters at that speed. We're still going at least that speed. It's like the baseline. So that going 50 meters per second for 4 seconds gets us 200 meters. This acceleration's like on top of that and gets us to go an additional 80. So you have to think of these conceptually and picture what's going on. And again, that one is because we started with some initial velocity. We didn't start at 0. I wrote it as this, but you can think of it as the initial velocity times time. That's the complete equation if you go on in physics. So basically, here's how far you go due to the acceleration part, and this is how far you went due to the velocity part, because you were already traveling 50 meters per second. Does that help with some of those? Has anybody figured out a height yet by counting the time down? Well, it doesn't come up every day when you're on a bridge or dropping rocks down a well, I guess. How about next thunderstorm? Probably repeat this when we get to sound and whatnot, but you see the lightning? And several seconds later you hear the thunder? That's because light travels faster than sound. You know this, no surprise. If you knew the speed of sound, distance equals rate times time. It's not going to be accelerating. If you know how the speed of sound, and you count for so many seconds, you know how far away the lightning strike was. Roughly, about 5 seconds is about a mile, given the speed of sound. Or now you can work it backwards and approximate the speed of sound. You guys are clever. I figure if some of you want to know, you'll go Google what the speed of sound is. But once you got that in your head, you don't have to remember what the speed of sound is. You just kind of remember that, about 5 seconds. Flash! 1001, 1002, 1003, 1004, 1000. Oh, it must be a mile away, roughly. Because it's traveling at a constant speed. Okay, maybe that helped. While we're doing that, did anybody think of some other questions? Yes?
On the homework, there's a problem about like a spring between 2 parts, and when I think about it, like in my head, it makes sense because the spring is going to push each part equally. So like, how would I say that in words?
So if the spring's compressed and you release, you know they're going to push apart? Well, what's this spring doing to that cart? Exerting a force. So force, you could say spring on cart. And that will tell you the motion of this cart based on its mass. Likewise, if you want to know the motion of this cart, same game over here. Spring on cart, but in the other direction. The reaction pairs to these are the cart pushes back on the spring on this side, as well as this cart pushing back on that spring. But Newton's third law with these action-reaction pairs, the spring's pushing on the cart, trying to expand back out. We'll get in chapter 7 that we've stored energy in the spring, but compressing it. And it has the potential to release that energy it does so by pushing on the block and giving the energy to the blocks. And they now have energy of motion. I just bring that up as a transition because that's what we'll do after the exam. Others? Yep. Question 2. Gravity on the moon is only 1/6 as strong as gravity on the Earth. So gravity on the Earth is 10 meters per second. Gravity on the moon is 1/6 of that. Again, I like writing down what I know. It helps me later when I'm thinking about it. What is the weight of a certain massed object on the moon and on the Earth? Again, we put different numbers in all of them. Let's say it's 14 kilograms. Whoop. All right, first one was, what is the weight of a 14 kilogram object on the moon and on the Earth? All right, how do we find it on the Earth? That one should be easier, I hope. Yeah, it's mass times acceleration, Newton's second law. We want to know how mass is affected by this force or this acceleration. That's the relationship. And the acceleration on Earth is that. So that would be 14 kilograms times 10 meters per second, which is, so on Earth it would weigh 140 newtons. I hope you can all do that by now. Or backwards, if I gave you the weight, could you figure out the mass? All right. Well, I'll just put in 1/6 of 10 for the moon. Gravity on the moon. So 14 and 10 over 6. You can dig your calculator out, but I just, half of that's 5, half of that's 3. 14 times 5, 20, 70 divided by 3. 60 would be, it's about 30 something. And that's probably how I give it. 20, thanks, see? Now we got it exactly. 23 newtons. A lot less. Sorry, I'm just thinking of what I wanted to tell you next. I don't think it matters. And then the easy question. Does the mass change? No. So it'd be 14 kilograms on both places. Others? Yep.
I'm not sure which question it is, whatever it is, the apple weighs 1 Newton at rest on your head.
Oh, yeah. There we go. The net force on this book is? 0. Does that mean no force is being applied? No, absolutely not. I'm pushing up. Earth is pulling down, but they're balanced. They're equal and opposite, so the net force is 0. And then when I throw it, if I released it, okay, while it's falling, what's the forces on it then? Just Earth pulling down on it. So there's only one force down. It's moving down, so there must be a net downward force due to gravity. And what would that be? If I gave you its mass, then times acceleration of 10 meters per second down, you'd have its weight. That's the only force. It's its weight. What is the net force would be that, because that's the only one. And if you actually need to know the value, you'd calculate it. Now, if there's air resistance, And the problem would say whether you can neglect or not. Then there might be some air resistance up. And now the net force would be its weight down minus air up. And I'd have to give you some more info. But does that help? What's the net force on it when I throw it up? Right at the top. Yeah, this is easier. Right there when it stops. Right there when it stops. What's the net force on it? Bless you. Yeah, it's not zero, is what you didn't say. It's still its weight. Because even though it's at the top and not moving, Earth is still accelerating it down based on its mass. So yeah, it's weight down. That's the force it feels. Actually, that's the force it feels on the way up, at the top, and on the way down. Because it's always being accelerated down. Even though it's moving up, stops, and moves back down. We didn't turn off gravity, the acceleration due to gravity. Yeah, let's do another demo. We've talked a bit. I hope this is helping you guys. All right, this can slide on here. And I'm going to hold the PVC, and I'm going to smack the block. What will happen to the red block? It'll slide down. See? Geniuses. Inertia. If both the PVC pipe and the red block are moving, things in motion want to stay in motion. If I stop the PVC pipe, boom, well, the red block wants to stay in motion. And so it slides a little until friction slows it down. All right. What if I hit the top of it? Still go down? Not move at all? Maybe go up? Reason it through. Yeah, I'm going to hit it, so I'm going to try to move both of them down. I'm going to try to hold still and just go. That's what I'll do. Well, we'll try that next. So, these are at rest. Things at rest want to stay at rest. And I'm going to exert a force directly onto the PVC pipe, trying to move it down. The block will want to stay put. So relative to the pipe, the block will move up because it's trying to stay put while the white pipe is moving down. Let's see. So see, your initial gut reaction was correct. And then you guys started cringing. All right, let's try. Okay, start in the middle. Now if I same idea. Again, we're moving. I stop the pipe, but the red block wants to keep going, so it scooches up a little bit. I think that's fun. And that's actually, see, something new generations don't get to appreciate quite as much. Wood hammers. And they slid the head on there. But when they become loose, because now they're all out of fiberglass and one piece or whatnot, but there's an easy way to tighten. There's several ways, but one of the simplest ways to tighten the head back onto the wood shaft. And you can shove things in there. You can get it wet. You can make a wedge. But the easiest is just do this. Now it doesn't wiggle. It's just this idea. Let's move them both. Wha-bam! Well, the shaft and the pipe stop, but the head and the block, see how I did that? Block, anyway, keeps moving and gets jammed on tighter. And it'll work for several more hittings, you know. And anytime it becomes loose, I just wham again, and it gets tight. Eventually, maybe you have to do a more permanent fix, but That was handy. Okay. This weighs 1,000. Rephrase that, Adam. This is 1,000 grams. That's its mass. Here's a spring scale. I'm going to weigh it. What will it read? When I lift this up, what will it read? 1,000 grams, which is 1 kilogram. 9.8, 10, yeah. Since we're doing real life, I expect it to be closer to 9.8 than 10. Let's see. Ta-da! Because the Earth pulls down on the block, makes it accelerate at 9.8 meters per second squared, times its mass of 1 kilogram, mg. So yeah, Earth pulls down at 9.8. So in order for me to hold it up, I got to exert a force on the scale of 9.8 up. What's its net force? 0. What's its acceleration? 0. Would we say this is an equilibrium or not? Yes. See, what else? How about way back when? You guys know the difference between fact, theory, hypothesis? I would review those definitions. Can they change? Yeah, with enough justification, absolutely. Yeah, but they get it. That's the best we know at this point. Okay, in the last few minutes, nobody's asked yet. I thought you would by now. What's the test going to be like? Well, here it is. It's multiple choice. They look just like every other question I've asked you on homework, pre-lecture clickers. I do use the bubble Scantron sheets, which, I didn't bring one in here. But if you, probably most of you have used them. You know where you circle the bubble for your answer? And that's what you'll turn in. So you'll get to do any work you want on here, but I'll grade the bubble sheet. There are 30 questions, unless your first thought was, I rarely have anybody that doesn't find that's enough time. Doesn't mean people won't stay the whole time, but there'll probably be somebody that leaves in 15 minutes. You know? And also, I want you to know that there will be 4 exams, and then there's the final exam. Of the 4 exams, there's no makeups. Well, you don't make up the final either. That one's set in stone. And I will drop your lowest exam. So, you know, some people just spaz out on tests. I understand that. Or you got a wedding. So if you miss one, do well on the other 3, and it won't matter. But the really good news is, for those of you that take the test Wednesday, you get the chance to make it up. I do make-up exams. So after class Wednesday, it'll become available on WebAssign, the exact same test. And you'll have until class on Friday to complete it. Now listen, if you want to, because I will average the grades if you make it up. I do this for 2 reasons. One, I would like you to learn this stuff. You know, you take a test, you bomb, you never look at it again. Well, this way it gets you to look at it. But 2, I think where you're happy is if you bomb it, it's a chance to make up some points. And you can get up to half the points you missed by retaking it. Open book, you go home, talk with your friends. So let's say you get I don't know, 70% on exam day. If you go and make it up and get, you know, ideally 100%, then I will average the 2 and you get right in the middle, which my fun brain, what is it, hex 30, 15, 85. That's what you would get. But only if you choose to retake it. I'll remind you Wednesday, but you don't have to, because it very, very rarely happens that somebody does worse on the makeup. I will still average the grades. What do you want to ask?
Yeah, I was asking, like, so if you do worse on the makeup, it's still.
But generally, because it's open book and you have more time, everybody can go figure out the answers.
Did you know your score before Friday?
You will not know it to decide, so it'll be on the field, yeah, because they don't get graded that fast.
Yeah,
That's the only catch, I guess. But I wanted to let you know that before you go stress out too much before Wednesday. Oh, yes. Yes, I do allow one size cheat sheet. You can put down some formula. You can put anything you want on one piece of paper. Thank you. I did forget to mention that. Yeah, I do allow that.
Front and back or just front?
Front and back's fine with me.